3 of February March 2021, past paper 4. So let's get started. Now in the first, so we are continuing with the previous video. I'll share the link in the description of the previous video. Now moving on, it says calculate the value of the rate constant k using data from experiment 4 and your answer to D part 2. So we know that the experiment 4 is this one, and the answer is, so basically we need the rate equation for this, and the rate equation was let me write it down again. So it was rate is equal to k, which is the constant, rate constant, which we need to find out, and the concentration for H2O2, sorry, H2O2, and concentration of IO3 minus. So that's the charge on IO3 ion, basically. It's iodate ion, if I'm not wrong. Okay, so this is the formula used. Now what we need to do is so what's the rate for experiment 4? So the initial rate is 8.82 into 10 raised to power minus 5. So what do? We use this formula, and okay, so we write 8.82 multiplied by 10 raised to power minus 5, right? Which is equal to, so then we write k, which we need to find out, and then we write the concentration for H2O2, which is 0.5 in experiment 4. So 0.15, sorry, 0.15, and then we write the concentration for IO3 minus. So they're both first order reactions, and what's the concentration for IO3? It's 0.14. Okay, so it is 0.14, bracket close. Okay, now what we do is we need to make k the subject, and after we multiply 0.15 and 0.14, we get, let me calculate it. So we get 0.021. all right, so we write 8.82 multiplied by 10 raised to power minus 5, which is equal to k multiplied by 0.021. Okay, now we need to calculate k, which means we need to make this the subject, right? Now if one number is being multiplied on one side, it should be divided by on the other side, right? So we divide 8.82 by 0.021. So we get the answer, which is 4.2 multiplied by 10 raised to power minus 3. That is the constant, rate constant. Okay, I hope you understood. Now we need to calculate, so it's also asking the units for k. Now okay, so what's the final equation after we make k the subject? So it's rate divided by rate divided by concentration of both of these, right? So it's concentration of H2O2 and concentration of IO3. So both concentrations, concentration, both concentrations, which is equal to K, the units for K. Alright, so what are the units for rate? So if you don't know, they're written over here, which is moles per dm cube per second. Okay, now we write, um, let me write it down. Okay, so it is moles. Okay, let me write it down. So we have mole, uh, and we draw a line over here, and then we write dm cube, because it says per dm cube and per second, so it should be divided, right? Okay, yes, this is 1 second, so we don't write 1 over here. Now we this is rate. These are the units for rate, and it should be divided by the both concentrations. The okay, so when we so now we put a dividing sign over here, right? And now what do? We write, so we multiply both of the concentrations. So when we multiply the two concentrations, the units for two concentrations, we get mole square, because there are two. So when we multiply moles by 2, we get mole square. So when we multiply moles by moles, we get mole square. That's how you get mole square, right? And when we multiply dm minus 3 with dm minus 3, we get dm minus 6. Sorry, we get yes, we get dm minus 6. So we write dm minus 6, right? So now if we write this like we did in rate, so what do? We write dm 6 over here. Now since these both are being divided, so when we take reciprocal, one of them will be inverted. So this one would be, okay, so this one would be dm6, and this one would be mole 2, mole square basically. Okay, now what do? So basically now we eliminate, so now it's multiplication sign, now we can cancel the 2. So mole is cancelled by one of the moles, so 1 mole is left over here, and dm cube is cancelled by dm cube as well, so dm cube is left over here, and over here 1 second is left. So what's the final answer? So it's let me write it. So it's dm cube, and we draw a dividing line, and then it's second and mole. So if I need to write it in the form like this one, so we write moles per dm cube and whatever. So we write mole per mole, basically mole minus 1 raised to the power minus 1 per second and dm cube. That's how you write it. Alright, I hope you understood it. And moving on to the next question, let me see if I need this. No, we don't. So let me erase this. Okay. Now moving on to the solubility product, it says lead iodide is only sparingly soluble in water at 25 degrees Celsius. The solubility product of this is 3.69 into 10 to the power minus 13 mole cube dm minus 9. Okay, write an expression for the solubility of PbIO3 2. Okay, now first we need to write the equation for the solubility product. So what do? We write Pb plus IO3, IO3, oops, IO3, and so it's Pb plus 2. Is it Pb plus 2? Yes. Pb plus 2 plus IO3 minus 1, which gives us, where is the arrow? Okay. After which we get this thing, PbIO3 2. Now over here in this one, in the final formula, there is 1 mole of Pb and 2 moles of IO3. So we write 2 over here to balance the equation. Alright. Now what do? So we write the equation for solubility product first. So we write Pb plus 2 concentration and basically IO3 minus 1. So I'm just writing I, but you should write IO3 minus 1 complete. And since there's a 2 over here, we raise it to the power of 2. We don't multiply it with 2, we raise it to the power of 2. Okay, so this is the expression for the solubility product. Now it says we need to calculate the solubility. Okay, so this is the solubility. Okay, now what do? So we write the okay, so we assume that the solubility of Pb plus 2 is x. Alright, and what is the solubility for IO3 minus 2? So basically we have 2 moles, so we multiply this by 2x, and because the concentration is squared, we write squared over here. Alright, now what's the, okay, and which is equal to, what's the solubility product? It's 3.69 into 10 to the power minus 13. So we write this over here. Okay, now when we open these brackets, so we get 4x squared, right? 4x squared. Now when we multiply 4x squared with an x, we get 4x cube, which is equal to this again. Okay, so now what do? We divide this thing by 4 and then take a cube root of that answer to calculate the value of x, and that's how you'll calculate the value of x. Okay, now moving on, So this one says this compound is unstable that readily decomposes when warmed. The decomposition reaction is shown. All right. This is the enthalpy change, which is minus 154.6 kilojoules per mole. Use the data in the table to calculate the entropy change of reaction. Now, how do we calculate entropy? Okay. So it's no, we need to find the change in entropy, right? So we okay, so first we draw a triangle which shows a change in entropy, and we write S over here, which is equal to final entropy minus initial entropy. Okay, the entropy of the products, and then minus subtracted by entropy of the reactants. Now these are all of the entropys are given over here. So what do? We add, so it's nitrogen, oxygen, iodine, and H2O in their products. So we add these, all of these, okay, but they depend upon the number of moles over here as well, because over here it's given per mole, but over here it's just half a mole. So we divide these, we divide these three entropies, so basically these three entropies, by 2 separately, and then because this is 2, so we multiply this by 2. Okay, so we get the answer. um okay, let me, so it's hit. So if we do 192 plus 205 plus 261, which we divide by what, which we divide by 2, yes, okay, and plus 2 multiplied by 70, which is 140. That's the entropy. The total answer would be the entropy for what, the final entropy of the products. Now when we've calculated that, whatever the answer is, we're assuming it's x right now, okay, and what's the entropy for NH4IO3, it would be 42. It won't be multiplied or divided by anything because over here it's just 1 mole. Alright, now it's 42 over here, so we subtract the final entropy with the initial entropy, so x minus 42, and whatever the answer we get, that would be the answer. Okay, now moving on, it says this reaction is feasible at all temperatures. Explain why using the data in F and your answer to Fi. Okay, so we need to explain why is it feasible. Okay, so we know that when is the okay, so we know when is the reaction always feasible, when the Gibbs energy, which is represented by G, is always negative or always less than 0, and this thing, what is this? This is entropy, which is always greater than 0, and the enthalpy change is also less than 0, like this. So they're both so this shows that it is an exothermic reaction, and this shows that it is just feasible, it's positive, and this is the overall Gibbs energy basically. So we need to mention all of these. That's why they're all feasible, because Okay, let's look at. So the answer which we calculated, it must be positive. That's why we know it's feasible. And the enthalpy change over here is minus 154, which means that it is an exothermic reaction. So the Gibbs energy should also be what? Um Negative, and so basically it should be less than 0. Okay. Now moving on, it says state the meaning of transition element. So we need to know the definition, the exact definition. So it is an element that forms one or more stable ions Okay, now it says that one d orbital from the lower energy level in an octahedral complex and one d orbital from the higher energy in an octahedral complex. Now we know that the lower energy levels, the orbitals are in between the axes. All right. So we draw, we can draw any of the two orbitals being in between axes. but I drew this. Alright, you can also draw one over here and one over here. Okay, sorry. This is on the axis, this is not in between axis. So we draw one over here and one over here, or we can draw one over here and one over here and one over here and one over here. Alright, so there are three options. Now on the higher energy level, it is on the axis, so it's one over here and one over here. So they're both on the axis. Or we can also draw, so there are two options for this one. So we draw this and we draw one circle over here, so we know it's on the axis as well, on this axis basically. Okay, now moving on. This is EDDS 4 minus and EDDA 4 minus are polydentate ligands that form octahedral complexes with Fe3 aqueous. The formula of the complexes are these respectively. Okay. On the diagram of EDD4 minus, circle each atom that forms a bond to the Fe3 minus in okay. So in this one, what do? We circle each atom that forms a bond to the Fe plus 3 ion. Okay. How are we going to figure that out? So we know that it will form one, so it will form four compounds with these oxygens, right? Because they're negative, and when they lose the protons for NH, both amine groups, so they'll form one with iron as well and nitrogen. Okay, so these are all of these that will form bonds. Okay, now moving on, it says FeEDDS is red and this is yellow. So we need to explain why they do have different colors. Now this is a very general question and we need to answer it generally. So why do two complexes have different colors? We just answer that generally. So basically the reason is that the d orbitals have different energy gaps, which means that they both have different frequency or a different wavelength of light is being absorbed. Okay, so that's the reason why. Now moving on, it says when EDDS4 minus is added to Fe3 plus, the following reaction occurs. This is the reaction. Now we need to tell what type of reaction is occurring over here. Okay, we need to observe how is this going on. So it's FeH2O6, which is then added to EDDS4 minus. This H2O6 is replaced by EDDS4 minus, which means the ligand is being exchanged. The ligand is being replaced. It's being substituted. So what's the reaction? We can call it anything. So basically we can call it ligand exchange, displacement reaction, displacement reaction, substitution reaction. We can call it any of these. Okay, now moving on. Now we need to write an expression for the stability constant K stab of FeEDDS. Okay, how do we write the stability constant? So we write products over reactants, right? But we don't mention H2O. We don't. Okay, so what would be the what would be the uh, equation? So it would be FeDDS divided by FeH2O6, and which will be multiplied in the denominator by EDDS4 minus. And don't forget the square brackets, otherwise you'll lose marks. Okay, now it says the table shows the stability constant of both complexes. Give me a minute. I just want to see how much of it is left. So, okay, it's quite long right now. Okay, so what do? We predict which of these are more stable. So, okay, so over here we know that, okay, so we look at the powers first. It's 25 over here and 20 is over here, which means that this is more stable, right? So we just write that FeEDTA is more stable because it has the value of K stamp is higher than the one of FeEDDS minus. That's it. That's what you write. When an excess of EDTA4 minus is added to EDDS, okay, the following equilibrium is established. Calculate the equilibrium constant for this equilibrium using the K stamp values given in the table in C5. Okay, so what do? We need to calculate the equilibrium constant. So the formula is, so write Kc is equal to, so basically first the one of the on in the products, so it's products over reactants, the K stamp values. All right, so we write constant basically K stamp EDDA, which is divided by K stamp what EDDS. You need to write it clearly with the brackets and all, but I am not doing that, but you should. Okay, I am not doing it to save time. Now what's the value for K stamp EDTA? Let me scroll it up. So EDTA is 1.26 into 10 to the power 25, and it should be divided by 3.98 into 10 to the power 20, and whatever answer you get, that would be the answer. Okay, I think we'll do this in the next class. Question number 5. I think we did 2 questions today. So 4 and yes, almost 2 questions. 1.5 basically. So we'll do the rest of it tomorrow. And I hope you understood today's class, and if you did not, you can ask me the questions in the comment section and I'll help you out. Bye bye. Have fun.